In this lecture, I am going to explain briefly the formula to be used for the analysis of member without translation of joints, then the detailed theoretical expression derived for the analysis of member with the translation of joints, then how to analyze the frame with the lateral translation of joints and the frame subjected to vertical loading and horizontal loading. First, coming to what is the expression used for the analysis of member without translation of joints. For the member without translation of joints, the final moment can be determined by using these two formula. So for AB member, the moment MAB can be determined, that is equal to MFAB plus twice M dash AB plus M dash BA. So MFAB is the fixed end moments and 2 M dash AB is the near end rotation moment, M dash BA is the far end rotation moment. Similarly, the MBA can be determined, that is equal to MFBA plus twice M dash BA plus M dash AB. So MFBA, this is the fixed end moment at the end B, and 2 M dash BA, this is the near end rotation moment, and this is the far end rotation moment. The moments M dash AB and M dash BA are called the rotation contribution, or this is called the rotation moment. This is called the rotation moment. The final moment, that is equal to the fixed end moment plus twice the rotation contribution of near end plus 1 the rotation contribution of the far end. The rotation moment can be determined by using this formula. M dash AB is equal to minus half KB divided by summation of KB into MFA plus summation of M dash BA, where minus half into KB by summation of KB, this is the rotation factor, and that you can denote by UAB. So UAB is equal to minus half into KB by summation of KB. So the rotation moment, that is equal to M dash AB is equal to UAB into MFA plus summation of M dash BA. The near end rotation moment can be determined by using the rotation factor and the fixed end moments of the joint and the far end rotation moments. But at the beginning, the far end rotation moment is assumed to be 0, and what is the fixed end moment of the joint, that you have to use. Then you can find out the near end rotation moment by using this formula. So these are the formulas used for the analysis of member without translation of joints. Then coming to what is member with translation of joints. We know that one of the supports of a continuous beam may sink due to subsidence of soil, or a frame may move sideways under wind or earthquake loadings. This lateral movement of the frame is called a sway. By sinking or swaying, the joints move in the direction of loading. This movement is called a translation. So in this section, we will discuss what is the effect of translation of joints on the actual end moments of members. So here coming to the analysis of member with the translation of joints. So look at the figure. So this is the member AB before translation of the joints A and B, and this is the member after translation of joints A and joint B. So the joint A translate to this position and joint B translate to this position. So here the displacement, that is at joint A delta A, and the displacement at joint B, that is delta B, and the change in displacement between A and B, that is equal to delta. And M double dash AB and M double dash BA is the translation moments at the end A and B. The above figure shows a member AB in a frame which has undergone lateral displacement at A and B. So that the relative displacement is delta, and delta is equal to delta B minus delta A. It may be noted that the ends are restrained from rotation. Here both ends are fixed, so the rotation at both ends, that is equal to 0. Theta A is equal to 0 and theta B is equal to 0. The fixed end moments corresponding to the displacements are m double dash AB is equal to m double dash BA is equal to minus 6EI delta by L square. The fixed end moments due to the displacements, you can find out the fixed end moments corresponding to this displacement are m double dash AB is equal to m double dash BA is equal to minus 6EI delta by L square. When the translation of joints occurs along with rotation, the true moments can be calculated by using this formula. The true end moment MAB is equal to MFAB plus twice into the near end rotation moment plus once into the far end rotation moment plus the translation moments m double dash AB. Similarly, the end moments MBA is equal to MFBA plus twice into the near end rotation moment plus once into the far end rotation moment plus the translation moment m double dash BA. So m double dash AB is equal to m double dash BA is equal to the displacement moment of member AB. Look at this figure. So here this is the frame, multi-story frame. So A is a joint where two or more members meet. So here there are four members meet: AB, AC, AD and AE. Then for condition of equilibrium of joint A, the summation of moment MAB is equal to 0. The summation of MAB is equal to 0. As you know, the equilibrium of joint A, that is the summation of the end moment MAB is equal to 0. So here, this expression is applied to all the members which are meeting at the joint A. So for this member AB, MAB is equal to MFAB plus twice into M dash AB plus M dash BA plus M double dash AB. Similarly, MAC is equal to MFAC plus twice M dash AC plus M dash CA plus M double dash AC. And for AD member, MAD is equal to MFAD plus twice into M dash AD plus M dash DA plus M double dash AD. And for AE member, MAE is equal to MFAE plus twice into M dash AE plus M dash EA plus M double dash AE. This formula can be used to all the members which are meeting at the joint A. So summation of MAB is equal to 0. As you know, this is the formula MFAB plus twice M dash AB plus M dash BA plus M double dash AB. Here the summation of this also equal to 0. Summation of MFAB plus summation of 2 M dash AB plus summation of M dash BA plus summation of M double dash AB, that is equal to 0. Then after simplification, you can find out the rotation moment summation of M dash AB is equal to minus half into summation of MFAB plus summation of M dash BA plus summation of M double dash AB. But we know M dash AB is equal to KB by summation of KB into summation of M dash AB. You have to put this expression of summation of M dash AB in this equation. So here M dash AB is equal to KB by summation of KB into minus half summation of MFAB plus summation of M dash BA plus summation of M double dash AB. Here, and M dash AB is equal to minus half into KB by summation of KB into the summation of MFAB, that is equal to the fixed end moment at the joint A, MFA, plus summation of M dash BA plus summation of M double dash AB. By using this formula, so you can find out the rotation moment. So the m dash AB, that is equal to minus half into KB by summation of KB. This is the rotation factor, so that you can denote by UAB. Then the formula m dash AB is equal to UAB into the fixed end moment at joint A plus summation of m dash BA plus summation of m double dash AB. So this is the summation of the far end rotation moment. This is the fixed end moment of the joint A, and this is the summation of the displacement moment or translation moments. Similarly, the m dash BA can be determined UPA into MFB plus summation of m dash AB plus summation of m double dash BA. So by using this formula, you can find out the near end rotation moment of the member or the frame when the translation of joints takes place. So first, coming to frames without lateral translation of joints. The frame in which lateral translations are prevented are analyzed in the same way as that of continuous beam, except that there may be more than two members meeting at the joint in the frames. While computing the rotation factors and rotation moments, all the members meeting at joints must be considered. As you know, the analysis of member without lateral translation of joints, the similar way you can also analyze the frame without lateral translation of joints. Then coming to what is the frames with the lateral translation of joints or sway. So look at this figure here. This is the unequal column height. So due to the unequal column height, the sway of the frame takes place. And look at this figure here. This is the unequal column stiffness. So due to the unequal column stiffness, the sway of the frame takes place, or the lateral translation of the joints takes place. And here look at this figure here. This is the unsymmetrical loading. So due to the unsymmetrical loading, the sway of the frame takes place. These are the frames with lateral translation of joints or sway. If a frame has unsymmetrical geometry and unsymmetrical loading, the sway takes place, causing the relative displacement at the end of the columns. This lateral sway causes additional moments which may be called displacement contributions. So the analysis of frames with the lateral translation of joints or sway, that you can carry out for the two cases. One, when the height of all column in a story are the same, and when height of column in a story are different. Look at these two figures. So here the height of the column of a story are same, but here having the unsymmetrical vertical loading, here having the horizontal loading. So due to this, the sway of the frame takes place, and due to this, the sway of the frame takes place. And look at this figure. Here the height are different. So this is unequal column height, and due to unequal column height, the sway of the frame takes place. In this section, first we will discuss, so when the vertical load is acting on the frame and when the horizontal load is acting on the frame, how to analyze the frame with lateral translation of joints. So analysis of frames with sway when all columns in a story have same height. So here all columns in the story have the same height, and when the vertical load is acting. So this is the frame having same column height in all stories. 1, 2 vertical column, 3, 4, 5, 6 and 7, 8. This is the column 1, 2 in a building frame, and this is the horizontal loading or lateral loading, and this is the moment which is acting at the end of the column 1, 2. Here the moment M12 and here the moment M21. Consider the frames shown in figure 1. Such frames are subjected to vertical load. Let 1, 2 represent a vertical member in any story of a multi-storied frame as shown in figure 2. Let 1, 2 is the vertical member in any story of a multi-storied frame. M12 and M21 are the end moments at 1 and 2. M12 and M21 is the end moments at the end of the vertical member. Let the horizontal force exerted by the frame on column be H. If the height of the story is H, small h, height of the story is given small h. From the equilibrium consideration of member 1, 2, the summation of M1 is equal to 0. So here you know, this is the vertical member. Take the moment about the joint 1. So this is clockwise, and this is also clockwise. So M12 plus M21 plus capital H into small h is equal to 0. Then capital H is equal to minus M12 plus M21 divided by small h. This is the horizontal force exerted by the frame on column. H is equal to minus M12 plus M21 by small h. So this is equation 2. In figure 1, let 1, 2, 3, 4, 5, 6, 7, 8 represents column in a particular story. So in a particular story, so 1, 2 is one column, 3, 4 is another column, 5, 6 is another column, and 7, 8 is another column. In this story, so these are the columns. Applying equation 2 to all column of the story. So this is the horizontal force exerted on the column. Apply this horizontal force to all columns of the story. So the summation of H is equal to minus summation of M12 plus summation of M21 divided by H. This is equation 3. Summation of H is the shear in all the columns in that story is equal to QR. So QR is equal to shear in the earth story. So you have to take summation of H is equal to QR. So QR is equal to minus summation of M12 plus summation of M21 divided by HR. HR is the height of column of the earth story. Then summation of M12 is the sum of the end moments of the upper ends of all the columns in the earth story. And summation of M21 is equal to sum of the end moments of the lower ends of all the column in the earth story. As the external loading is vertical, so QR is equal to 0. The horizontal shear that is equal to 0. So all the columns of the earth story are of height HR. Therefore, we have from equation 4 as QR is equal to 0, summation of M12 plus summation of M21 is equal to 0. This is equation 5. For the earth story, we know the general expression for end moments for member 1, 2 is equal to M12 is equal to MF12 plus twice into the near end rotation moment plus once the far end rotation moment plus the displacement moment or translation moments M double dash 1, 2. Similarly, M21 is equal to MF21 plus twice M dash 21 plus M dash 1, 2 plus M double dash 21. This is the expression. So by using this expression, you can find out the end moments per member 1, 2. As the column is vertical, there is no horizontal loading. So MF12, MF21 is equal to 0 since the loading on the frame is vertical. For any prismatic member, so here you see MF12 and MF21 both are 0. As the load is acting vertically, there is no horizontal loading. So the fixed end moment on the vertical member 1, 2 is equal to 0. MF12, MF21 is 0. For any prismatic member, it may be noted that M double dash 1, 2 is equal to M double dash 21. M double dash 1, 2 is equal to M double dash 21. The translation moments or the displacement moment M double dash 1, 2 is equal to M double dash 21. Therefore, the summation of M12 plus summation of M21 is equal to, so here you take the M12 and M21. So after taking the summation of these two, finally 2 M dash 1, 2, here 1 M dash 1, 2, 3 M dash 1, 2, and here 2 M dash 2, 1, M dash 2, 1, 3 M dash 2, 1, and this is m double dash 1 2, this is both are equal, so twice into m double dash 1 2. Summation of m12 plus summation of m21 is equal to 3 m dash 12 plus 3 m dash 21 plus 2 summation of m double dash 12. This is equation 7. Then you know from the equation 5, summation of m12 plus summation of m21 is equal to 0. Just you take this equation is equal to 0. 3m dash 12 plus 3m dash 21 plus twice summation of m double dash 12 is equal to 0. Then after simplification, so summation of m dash 12 is equal to minus 3 by 2 into summation of m dash 12 plus summation of m dash 21. This is equation 8. Equation 8 gives a relation between the rotation and translation moments. So this is the rotation moment, this is the rotation moment, and this is the translation moment. So this is the relation between translation and the rotation moment. The relative lateral displacement delta is the same for all the columns in any one story. For any column, the translation moment is equal to m double dash 12 is equal to 6ei delta by h square is equal to 6ei phi by h, where phi is equal to delta by h. Thus, the translation moment of a column in a story is proportional to their relative stiffness, and k is equal to the moment of inertia by length of the member. The relative stiffness of the member is equal to the moment of inertia by length of the member or height of the member. K is equal to I by h. Therefore, the m double dash 12 divided by summation of m double dash 12 is equal to k12 by summation of k12. M double dash 12 is equal to k12 by summation of k12 into summation of m double dash 12. As you know, summation of m double dash 12 is equal to minus 3 by 2 into summation of m dash 12 plus summation of m dash 21. So put this expression 8 in expression 9. Substituting summation of m double dash 12 from equation 8 in equation 9. M double dash 12 is equal to k12 by summation of k12 into minus 3 by 2 into summation of m dash 12 plus summation of m dash 21. Then m double dash 12 is equal to minus 3 by 2 k12 by summation of k12 into summation of m dash 12 plus summation of m dash 21, where minus 3 by 2 into k12 by summation of k12 is the displacement factor. So that you can denote by nu. So m double dash 12 is equal to nu 12 into summation of m dash 12 plus summation of m dash 21. Nu 12 is equal to minus 3 by 2 k12 divided by summation of k12, where nu 12 is the displacement factor, or it is also known as translation factor of a member. And the summation of m dash 12 plus summation of m dash 21 is the sum of rotation moment at top and bottom ends of all the columns of the story. And summation of k12 is the sum of the relative stiffness of all the columns in the story. The sum of the translation factor of all the columns of a story will be equal to minus 3 by 2. Always you have to check the sum of the translation factor of all the columns of a story, that should be minus 3 by 2. And the translation factor that you can find out by using this expression, nu 12 is equal to minus 3 by 2, the relative stiffness of the vertical member divided by the sum of the relative stiffness of the all the vertical members in the same story. Nu 12 is equal to minus 3 by 2 into k12 by summation of k12. K12 is the relative stiffness of the vertical members 12 divided by the sum of the relative stiffness of the all the vertical members of the same story. summation of K12. And this is the formula used to find out the translation moments. M double dash 12 is equal to the displacement factor into the sum of the rotation moments at the top and bottom end of all the columns of the story. This is the final summary. When the frame subjected to the vertical loading with the lateral translation of joints. So this is the formula used to find out the rotation moment. M-12 is equal to U12 into M1F plus summation of M-21 plus summation of M-12, and M-21 is equal to U21 M2F plus summation of M-12 plus summation of M-21. So this is the rotation factor, this is the fixed end moment of the joint, and this is the far end rotation moment, and this is the translation moment of the vertical member. The translation moment that you can find out, M-12 is equal to M-21 is equal to nu12 into the summation of M-12 plus summation of M-21. So nu12, this is the displacement factor or translation factor that you can find out by using this formula, minus 3/2 into K12 by summation of K12. K12, this is the relative stiffness of the vertical member, and this is the sum of the relative stiffness of all the vertical members of the same story. So this is the formula you can use for getting the translation moment. Then the final moment can be obtained by using this expression. M12 is equal to MF12 plus twice into the near end rotation moment plus once the far end rotation moment plus the translation moments. Similarly, M21 is equal to MF21 plus twice M-21 plus M-12 plus M-21. So this is the formula. So by using this formula, you can find out the rotation moments, then translation moments, then you can find out the final moments. Then coming to the frame with the lateral translation of joints and the frame subjected horizontal loading. This is the multi-story frame, and this is the horizontal shear H. This is shear in columns, and this is the earth story, and the height of this story is HR. And for frame subjected to horizontal loading, the story shear summation of H is equal to QR. If all the columns of the story of height HR, all the columns of the story of height HR, we can write the equilibrium equation summation of M is equal to 0. As you know, the moment for these vertical members, that is summation of M12 plus summation of M21 plus QR HR is equal to 0. Already we got this expression here, this one, M12 plus M21 plus H into H is equal to 0. So here, summation of M12 plus summation of M21 plus QR HR is equal to 0. Then QR HR is equal to minus summation of M12 plus summation of M21. Then from equation 7 and put in equation 15. This is equation 15, and from equation 7, as you know, in equation 7, the summation of M12 plus summation of M21 is equal to 3M-12 plus 3M-21 plus twice summation of M-12. Put this expression here. Then QR into HR is equal to minus summation of 3M-12 plus M-21 plus twice M-12. This is equation 16. Then divide the equation 16 by 3. QR HR by 3 is equal to minus summation M-12 plus M-21 plus 2 by 3 M-12. Then find out the summation of M-12 1 2 is equal to minus 3 by 2 QR HR by 3 plus summation of M dash 1 2 plus M dash 2 1. This is equation 18. Then summation of M double dash 1 2 is equal to minus 3 by 2 MRF. So this is QR into HR by 3 is equal to the MRF. So this is known as the story moment. This is known as the story moment. So minus 3 by 2 into the story moment MRF plus summation of M dash 1 2 plus M dash 2 1. So MRF is equal to QR HR by 3, known as story moment. Then the positive when Q act from right to left. So this is considered positive when this is acting from right to left. Then M double dash 1 2 is equal to K12 by summation of K12 into minus 3 by 2 the story moment plus M dash 1 2 plus M dash 2 1. Then minus 3 by 2 into K12 by summation of K12, this is the translation or displacement factor. So that you can denote nu 1 2, and the translation or displacement moment that you can find out, that is M double dash 1 2 is equal to the translation or displacement factor into the story moment plus M dash summation of M dash 1 2 plus M dash 2 1. So M dash 1 2 and M dash 2 1, this is the rotation moment of the vertical member of the same story. This is the sum of the rotation moment. This is the sum of the top end rotation moment and bottom end rotation moment of the vertical member of the same story. So nu 1 2, this is equal to minus 3 by 2 into K12 by summation of K12. So this is the translation or displacement factors. This is a summary when the frame subjected to the horizontal loading and with lateral translation of joints. So the rotation moment that you can find out, M dash 1 2 is equal to U12 M1F plus summation of M dash 2 1 plus summation of M dash double dash 1 2. So this is the fixed end moment of the joint, this is the far end rotation moment, and this is the translation moment of the column which are meeting at the joint 1. And M dash 2 1 is equal to U21 M2F plus summation of M dash 1 2 plus summation of M double dash 2 1. So U21 is the rotation factor. So this you can find out by using this expression minus half K by summation of K. Then you can find out the translation moments. M double dash 1 2 is equal to nu 1 2 MRF plus summation of M dash 1 2 plus M dash 2 1. So MRF is the story moment that you can find out by using this formula. MRF is equal to QR HR by 3, and nu 1 2, this is the translation or displacement factor that you can find out by using this expression minus 3 by 2 K12 by summation of K12, and this is the rotation moment of the top end of the vertical members and bottom end of the vertical members of all the columns of the same story. The final moment that you can determine by using this expression, M12 is equal to MF12 plus twice M dash 12 plus M dash 21 plus M double dash 12. Similarly, M21 is equal to MF21 plus twice M dash 21 plus M dash 12 plus M double dash 21. So this is the formula. So by using these formulas, you can find out the rotation moments, translation moments, and the final moment. Now all are clear how to analyze the members or the frames with the translation of joints when subjected to the vertical loading and horizontal loading.